In today's automation world, the requirements for a system are manifold and complex. Consistency across all three of the automation levels regarding information processing and communication are a prerequisite for successful realization of a plant. In the plant control level, for monitoring and controlling system-wide tasks, in the process control level, for controlling individual processes, and in the field level, for direct data recording and influencing the process. A large selection of these components, designed for a variety of problems, allows you to realize the optimal solution for the respective task. For the communication between the individual components, SIMATIC S7 offers a number of standardized, openly defined bus systems, tailored to the respective application area. These bus systems and their use for a certain task are evaluated by four basic properties: size of transferred data amount per job, real-time capability or determinancy of the data transfer, EMC loadability of the bus system, as well as design regarding maintenance and expandability. Industrial Ethernet is the standard in the LAN sector and is the technological base of the Internet. It is marked by its high transferable data amount. Originally designed for office environments, it shows a lower determinancy and EMC loadability. Profinet means Industrial Ethernet for process-oriented operation. Technological expansions, as well as real-time functions, help reach the determinancy demanded in automation technology. Using industrial components even enables application in field-related areas. The Profibus specified in the IEC standard is the worldwide most distributed field bus. Its high determinancy and EMC safety makes it the technological platform in the field bus sector. In the actuator and sensor communication sector, the ASI bus system offers a cost-effective alternative to the cable tree. It connects simple actuators and sensors by means of a two-wire line, via which data and energy is transmitted, and simplifies maintenance and later expansion. Apart from selecting the bus system, the type of communication also plays an important role. The communication functions of a SIMATIC S7 controller are divided into three classes. The I/O communication occurs between the CPU of the automation device and the central or distributed I/O, meaning the actuators and sensors such as field devices, drives. In data communication, the automation devices communicate with each other or with other communication-capable partners, such as a PC. Process data, or recipes for example, are transmitted. System communication refers to integrated communication functions, via which the automation devices can communicate with HMI devices or programming devices, in order to visualize a process or loading the system configuration into the CPU of the automation device. In the course of this demonstration system, we will discuss the communication classes in greater detail by means of selected configuration and application sequence. The communication relationship between individual stations and components of a plant must first be configured. The NetPro tool, integrated into the SIMATIC Step 7 development environment, supports you with its graphic procedure and clear display. NetPro offers you a comfortable configuration user interface, even for large and complex plant structures, direct access to the hardware configuration of individual components, direct addressing of interfaces as well as their assignment to bus systems, and configuration and diagnostics for communication connections of the data communication. In the following examples, we show you the configuration of the three communication classes, namely I/O, data, and system communication. We start with configuring the I/O communication. Due to the data exchange with actuators and sensors, it is closest to the In this case, we use an S7-300 CPU as Profibus DP master. 3 DP slaves will be assigned to it, an I/O module, a drive module, and a connection to the ASI bus. The S7-300 station with the Profibus DP master has already been configured to the extent that a DP master system can be inserted as a basis for I/O communication. Subsequently, we select the desired DP slave from the hardware catalog and connect it to the master system. The automatically displayed address dialog offers addresses for selection, which are still available in the respective Profibus network. Even for complex slaves, such as drives or a network transition, the allocation to Profibus Net and DP Master occurs in the same way. When compiling the project, NetPro checks whether all necessary details are given. In our example, a component in the SIMODrive slave drive module, which we insert in the Step 7 tool hardware config, is still missing. Here, the hardware catalog offers us all components permitted for insertion into the slave. The configuration of the ASI net can also be completed in hardware config, where we insert the required ASI slaves into the configuration table of the DP ASI link. For components not listed in the hardware catalog, or only listed in an older version, module information may be available some other way. Hardware updates of SIMATIC products or GSD files of external products can simply be included here. In order to complete the configuration, we update the database of station and buses for the entire project by means of save and compile. Apart from compiling I/O data, automation devices must also be able to communicate with each other. This is achieved by means of data communication. The various protocols can be used to communicate with a variety of communication partners, such as controllers, PCs, or third-party devices. An example are protocols such as FDL and FMS on the basis of Profibus, as well as the ISO transport or TCP/IP on industrial Ethernet. Within a homogeneous S7 environment, the S7 protocol is also available to us. Its extraordinary features are simple configuration, transmission of different data types, and independency of the bus system used. In this case, an S7 connection between an S7-300 station and an S7-400 station will be configured via TCP/IP. NetPro is again used for interconnecting the involved stations as well as the connection configuration. Networking can be accomplished in an uncomplicated and clearly displayed graphical manner by means of connecting the respective communication interface with the desired network. The so-called node initiation, which refers to the first-time allocation of a bus address, is necessary for all communicating stations, hence also for our communication partner S7-400. In order to insert a connection, we select the CPU of the affected controller. In the connection table, all configured connections of the selected CPU are displayed with additional information, such as connection type and connection partner. The connection wizard is called to insert a new connection. As a connection partner, we select the S7-400 station from our current project. Alternatively, the connection partner could also be part of a different project. Furthermore, it is possible to use a component unknown within Step 7, which must then be specified more precisely by the user regarding its connection properties. We select an S7 connection from the list of connection types available in Step 7. When confirming the dialog, Step 7 tests the selected connection regarding plausibility and reports an error if necessary. If no errors occur, the properties dialog of the connection opens. Here we find information on the used interface, the used bus system, and the respective address for both connection partners. The programming interface of the connection is displayed symbolically by means of block parameters. The save and compile function completes the configuration of the communication connections. We consider the system communication as a third communication class. The active communication partner, for example a programming device or an HMI station, uses the communication functions already existing in the operating system of the controller. As a first example, we are loading a user program into the CPU of the S7-400 station. Due to the fact that the programming device is connected to the Profibus, the S7-400 station on the other hand to the Ethernet bus, the online access is only possible using the operating function PG routing of the S7-300 station. Within NetPro, we insert our programming device into the project. The Properties dialog lists the interface configurations possible for the programming device. Intending to connect the programming device to the Profibus network, we first add a new Profibus interface. The node initiation occurs by means of selecting the Profibus network and determining the address. The address field automatically displays the remaining free addresses. Now the corresponding network card and configuration must be assigned to the interface. We select CP5611 Profibus and allocate it to the new interface. At the connection between the programming device and the bus system, now shaded in yellow, we can recognize that the S7 online access for the selected interface has been activated. We are now able to load the S7-400 station with a user program, even though our programming device is only connected to the Profibus. From there, PG routing and the routing-capable modules within the S7-300 station enable us to reach the station to be loaded via the industrial Ethernet bus. When loading the S7-400, the used network transition is displayed as an additional entry in the address dialog. The station with the Profibus address 2 is exactly our routing-capable S7-300 station. As a further application case, we consider an HMI system which as an active communication partner exchanges data with the controller. The operating system of the CPU already contains the functions necessary for it. Equal to the programming device, the HMI station is first inserted into the project. The interface with the bus system already exists and must therefore not be configured. The node initiation can be performed in a simple graphical manner by connecting the communication interface with the Profibus. Saving and compiling the project accepts the communication data into the joint database. It is then available, for example, for the configuration of the visualization WinCC Flexible. Next, we will discuss the user interface of the I/O and the data communication in greater detail. For the I/O communication, the data of the I/O devices are cyclically updated in the DP master by means of the master-slave method used for Profibus DP. Prior to each cycle of the user program, the current input data of the I/O are, from the DP master, loaded into the process image input table. After processing the input data, the results are written into the process image output table. From there, the output data are, after each user program cycle, transferred to the DP master. The access to the process images occurs per byte, word or double word by means of load and transmission commands, or bit by bit using logic operations. During data communication, there is no individual master which cyclically updates the data. The connection partners have equal rights. The configuration defines one partner as the active station that makes the connection. Sending the data can equally be triggered off by both partners. In the user program of the sending CPU, a send block is called, which first transmits the system data to the send buffer, and from there sends it block by block to the receiving CPU. In the user program of the receiving CPU, a receive block initially collects the data blocks into the receive buffer and then transfers them to the specified memory area. Due to the bidirectional nature of the connections between two S7 CPUs, both CPUs can send and receive at the same time. In the preceding sequences, you were familiarized with the basic communication mechanisms of the SIMATIC S7. You have seen which decisive advantages the SIMATIC S7 offers here. Consistent communication from field level to plant control level, flexible application options of various standard bus systems, a clearly displayed graphical configuration with NetPro, and simple communication programming within the user program.